Hi everyone. So today we're going to talk about electric circuits. Now this drawing here, made by me, is a typical electric circuit. It's got a battery and a wire, and it's got this tiny little lamp over here that's shining. And what we would like to know is why it shines. It turns out that what makes the light bulb shine is that there's electricity going through it. And remember that electricity is nothing but electrons. Remember, electrons are these little particles that have negative charge that live in atoms. So in the middle we have protons that are positively charged, and around it we have electrons that are negatively charged, and it's electrons that are tiny enough to move. Now, the reason that our light bulb shines when an electron gets through is that it's a little rough. And because it's a little rough, something like this, when an electron gets through, there's friction. And when there's friction, remember, the temperature of this thing rises. And when the temperature rises, light is emitted. If you manage this to get hot enough, it starts giving off light. And that's how incandescent bulbs work. Now, how much light this thing gives off depends on how much charge goes through the wire. Now, of course, we need a unit to measure charge, and the unit that we use is called the coulomb. Now, 1 coulomb is a lot of charge. Just think about this. One electron, the charge of one electron is 1.6 times 10 to the minus 19 coulombs. So there's billions and billions of electrons in only 1 coulomb. So when we say that 1 coulomb of charge has gone through a part of our circuit, like for example through here, what we're saying is that there's billions of electrons that have gone through. Just remember that a coulomb is an extremely big unit of charge. The symbol that we use to denote charge is Q, probably because C was already taken. So Q is the symbol for charge, and the units are coulombs, or C. Don't confuse the two. Now, normally I'm not really interested in charge. What I want to know is current. Now, current is just charge per unit of time. So imagine that I'm sitting here. Well, I'm not really sitting, I'm standing here. And I want to know how many electrons, or how much charge goes through this point in 1 second. Well, that's called the current that goes through this point. Okay, so how do I express this mathematically? Well, first thing, I'm going to have to define the current, or let's give it a little symbol, right? And in this case, it's the I. And I stands for intensity, which is the word that people used to use and still use in some universities for current. Okay, so this means current. Now remember that current is charge per second, right? So imagine that I know that 4 coulombs went through here in 2 seconds. How much charge per second went through here? Pause the video and answer in your head. Okay, well, if you did as I told you, you probably figured out that it was 2 coulombs per second, right? Because there was 4 coulombs in 2 seconds. So in your head, you divided, right? Therefore, the current has to be the charge that went through the place divided by the time that it took it, right? Now, what are the units for this thing? Well, let me zoom out for a second. All right, so let's take a look at the units. We know that current is charge over time, and we know that the units of charge, so units of current, remember that this means units. So units of current will be the units of charge divided by the units of time. And if you were listening before, you know that the units of charge are coulombs and the units of time are seconds. And therefore current has to be measured in coulombs per second. But because we're lazy to write this all the time, we give it a new name and we call it amperes, which we denote with the letter A. So current is measured in amperes. And this is basically the name of the guy who did experiments with wires and found out about magnetism and stuff. That's why we call them amperes. Anyway, current is measured in amperes, but remember that an ampere is just 1 coulomb per second. And how do we measure current? I mean, what if you want to do an experiment and find out how much current there is somewhere? Well, Simple. We use a device called an ammeter. So imagine that I have a wire, there's some current going through it that I don't know. Then I have to put this little device here called an ammeter that I will depict like this. Ammeter or ammeter. And then all I need to do is look at the reading of the ammeter and it will tell me how many amperes. So for example, 0.3 amperes. And there you go. Now we will discuss exactly how you need to place this thing to get the right readings later on when we learn about series and parallel circuits, which will probably not be during this lesson. Now we have to stop for a moment and talk about something that has very little to do with physics and a lot to do with history. Because, summarizing, we got unlucky. Now, here you see a battery and you see that it has a plus side and a minus side, right? So we need to assume that here there's way too many electrons, here's there's way too few, and therefore electrons want to go from this side to this side. Now in order to do this, they can't do so through air, so they have to do it through the wire because the wire is a conductor and air is an insulator, right? Therefore, the direction of current is the direction of the electron flow, which is this way, right? Well, you would think so, but actually, we usually say that current goes this way instead. Now, why on earth would we do this? Well, the problem is that when we were learning about electrons and so on, we really had no way to tell which one of the charges was the one that was moving. It could have been this one, could have been this one. So physicists made a gamble. Okay, let's assume that it's this one that moves, and let's just call this direction the direction of current. Now, later on, we find out that we got it wrong. We had a 50% chance, and we blew it. And it turns out that it's this charge that's moving. But it was too late, because textbooks had been written like this for hundreds and hundreds of years. So what do we do now? Well, we pretend that there's some positive charge moving from here to here, even though we know that what's really happening is the opposite, that there's some negative charge moving from here to here. Now, to this thing, the real current, we call it the actual current flow. So let me just write that down. Actual current flow. Well, actual current. And the one that we will use throughout this course, and is the one that you need to know, is the conventional current flow, which means it's not real, but it's just the one that we use by convention. So you need to know that the current flow in a battery is the opposite of what you would expect if you took into account that it's electrons that are moving. Okay, now I'm going to stop using this symbol for batteries, and instead I'm going to use this one, where the long stick goes for the plus side and the small stick goes for the minus side. And the reason I'm going to do this is that it's much easier to draw, and that actually you have to know this, because it's the standard circuit symbol for batteries. Now, what you usually call batteries, which is this thing, is actually called a cell in physics. And we use the name battery when there's several cells, one after the other. So remember, when you see this thing, that's not a battery, that's a cell. Many of them put together, that's a battery. Now, you may have been wondering why, if I have a circuit like this, and remember that current goes from plus to minus, so this is the current flow. You may have been wondering, why does this happen? Why would electrons go from here to here? And the explanation that I gave you before was that there's an excess of electrons here, and there's not enough electrons here, and then electrons just want to go to where there's less electrons. What actually happens is that between here and here, there's a potential difference, which hopefully you remember from the previous class. Now, the potential difference, we write it as V for voltage, remember? And the units are also volts, so the same letter, for the thing and for the units. And remember that 1 volt was just energy per unit charge. So 1 volt is 1 joule per coulomb. So the potential difference just told us how much energy per unit charge does this battery give the charges that we have inside. Okay? Now you can imagine a potential difference a little bit as if it was a difference in height, right? So I'm here, and here's a little cliff, and the higher the cliff, the faster I'm gonna go when I reach the bottom, right? And therefore, the more the potential difference, the more energies that the electrons are going to gain as they go around the circuit. In fact, the more potential difference, the more electrons I'm going to have going around here, right? This means that if I increase the voltage, everything else being equal, then the current is going to increase. In fact, if I double the voltage, then the current will double, and so on. So we can say that the current going through a wire is proportional to the voltage between the two sides of the wire. Now here comes a very subtle distinction between two concepts that are almost the same. One is called EMF, and the other one is called voltage. And I'm going to try to explain this slowly so that everybody gets there. Now, EMF stands for electromotive force. Electromotive, which means, or unless it looks like it means, that it's a force that makes things move, that makes electrons move. And that's kind of what it is, but it's not really a force. Actually, an EMF is just a potential difference, just like voltage. Okay? EMF is just, if I have a battery, remember batteries, the old way we drew them? EMF is just the energy per unit charge that this thing gives the stuff that's inside. Okay, so whatever you see on the battery written in here in a little label in here, that's the EMF. So for example, 1.5 volts. Okay. Now what happens is that if I have a circuit like this one, even though the EMF of the battery may be 1.5 volts, in practice, if I measure the potential difference between here and here, I'm going to get less. And the reason I'm going to get less is that just inside the battery, there's some friction for the electrons. So some of this energy that this thing is in theory giving my electrons is lost. Therefore, the EMF of the battery is not the same as the potential difference between its two sides, because some of this energy that it's giving me in theory is lost because of friction. Okay? Now in a lot of practical cases you don't care, and the EMF and the voltage are exactly the same if there's no friction inside the battery. But in some special cases this is not going to be the case, and you need to be able to differentiate between EMF as the energy that's given to each charge by the battery, and the voltage, which is just the potential difference between the two sides. Now we know enough to start drawing circuits. Now, of course, we could, draw them artistically, but because we're physicists and most of us can't draw, what we need to is a very, very simplified way of representing circuit elements. Now, you already know the symbol for the cell. And remember that a battery is just a bunch of cells put together. So that's the symbol for a battery. And remember, battery is not what you think it means. Cell is what you call a battery. Now, apart from these, of course, we have the symbol for a wire, which is just, a wire. And we have a symbol for a switch. Now, a switch is really easy to draw. It's just this. So, of course, this means closed switch, open switch. And finally, we need a symbol for a light bulb. Okay? Like this. Now, for example, we can use these symbols for drawing a circuit that has two light bulbs, one after the other. So, here's my battery. Here's my wire. I'm going to make a switch now. Light bulb, light bulb, and there we go. Here's a circuit. This is a very convenient way of representing stuff without, having to take an art class. We need to introduce now one last notion, and this notion is the notion of resistance, which we represent like this. And you can imagine a resistance like a door that lets electrons through more or less. Right? So if the door is very small, we say that the resistance is very high. So imagine that, I don't know, here's my electron who's trying to get through the door, but the door is this little, and then there's like lots of them. So, they're giving out, I don't know, free Coca-Cola or whatever. And so of course they want to get through, but they don't all fit, which means that resistance is actually limiting how many electrons go through a wire. If I put a resistance here in the middle, it's not going to let electrons go through as much as they would, and therefore the current that would go through the wire will be smaller than it would be if I didn't have the resistance. Now, the smaller the resistance, the bigger the door, and the easier it is for electrons to get through. So basically we have that the bigger the resistance, the smaller the current. Okay? Now, we can use this to come up with a mathematical expression for resistance. And for this we will have to use both the voltage, the current, and the resistance. Okay? Now let's think about this for a moment. Imagine that I want to know the current going through a circuit. So here I have a certain voltage, a resistance, and there's a current going around here this way, right? And I want to know the current. Now I ask myself, well, if the voltage is very big, am I going to get more or less current? Now if the answer is more, remember, this will be multiplying. If the answer is less, it will be dividing. We know that the more voltage, the more current, and therefore voltage must be multiplying. Now, if I get a lot of resistance, will I get more or less current? And we saw here that more resistance means less current, and therefore resistance has to be dividing. And hence we get this really handy equation that tells us that the current is proportional to the voltage and inversely proportional to the resistance. We can switch this around easily and get the resistance in terms of the other two, right? So resistance will be equal to voltage divided by current. And all I did here was move this guy here, move this guy here. And this is actually the definition of resistance. We define resistance as the ratio between the voltage between here and here and the current that goes through. Now we need to think about the units that we're going to use to express resistance. And again, we're going to do what we did before with current. The units of resistance, remember this little bracket thing means units, have to be the units of voltage divided by the units of current. Now, what are the units of current? Volts. Okay, good. Volts. And what are the units of current? I hear you screaming. Amperes. Okay. So the units of resistance are volts divided by amperes. But again, we're too lazy to write this all the time, so we just make up a symbol for this. And unfortunately, it's a Greek letter, the Greek letter omega. This is the unit of resistance, omega. And we call these units ohms. So resistance is measured in ohms. So 1 ohm is just 1 volt per ampere. Now I know this must be a little hard, so let's just do a little example, okay? Imagine that I have a circuit, and I just leave the equations here, and I have a circuit with, let's just put some numbers in here. So I have 4 volts, and I have a resistance of 2 ohms. And I ask myself, what's the current? Okay, well, I use this equation here. So current is voltage, 4 volts, 4 volts divided by resistance, 2 ohms, 2 ohms, and that's 4 divided by 2, that's 2 amperes. Done. Or we could do it the other way around. I could delete this. Okay, well, it doesn't really let me delete this. Sorry, let's do this instead. So I could do this. I could have 4 volts, and I could have a resistance that I don't know, but I could know that the current is 2 amperes. So what's the resistance? Well, in this case, I would use this equation, that resistance equals V divided by I, and therefore resistance will be, again, 4 divided by 2 equals 2, and what are the units? Yeah, ohms. The weird little letter that looks like a horseshoe. Okay, this was a very, very long video, and I promise we're almost done. But there's just a lot of stuff to study today. Now we want to learn about what factors affect resistance. Okay, now imagine that this is a piece of wire. Okay, normally a conductor, so a piece of conducting wire that has a certain resistance R. And what I want to know is, when does this thing get bigger? When does it get smaller? What do I have to do to this wire to increase or decrease resistance? Well, first thing that I could do, for example, is make this wire longer. So I could make this wire longer, and what would happen to the resistance? Well, you can imagine this like a little jungle, right? So the electron tries to get through, and it has to go through jungle. Oh, it's so hard, it's so hard. Now if I make this even longer, there's more jungle to go through, and therefore it's harder to get through, right? So therefore the more length, the more resistance. So if this is the length, this increases the resistance. So let's just say that resistance equals the length times some other stuff, and the length has to be multiplied because the more length, the more resistance. Now what happens if I make the area bigger? Well, if I make the area bigger, I'm actually giving the electrons more room, right? Because before they could go only through here, but now they can go through here too, right? So making the area bigger actually makes things easier for my electrons, and therefore the more area, the less resistance. So the area has to be dividing. Okay, so there we go. So the resistance has to be proportional to the length and divided by the area. And now we are only missing one number, and this little number is called the resistivity, and we're going to write it with this weird Greek letter. Okay, so I'm just going to make it big so that you can see, and this is called the resistivity. Now this number depends on the material. So some materials have a lot of resistivity, which means that they're very hard to travel through for your electrons, and some of them have very low resistivity, which means they're very easy to travel through for the electrons. So of course, the higher the resistivity, the higher the resistance. And here we have the formula for the resistance in terms of these three things: the resistivity, the length, and the area. Let me just add little arrows here so this is the area, this is the length, and this is the resistivity. Yep. All right. Now, knowing this, you could solve a problem. For example, imagine that I have a certain wire. So I have a certain wire of 2 meters. And I know that its resistance is 4 ohms. What happens to the wire when I make its length 4 meters? Well, the more the length, the more the resistance, right? So if I double the length, I will double the resistance. Therefore, the resistance will go to 8 ohms. Using this very simple idea, we can figure out the resistance of different lengths and areas of wire if we know the resistance of one piece. Alright guys, I won't show you the learning objectives today because I actually tried and it was such a huge list that I thought I would just scare you. Hopefully after this video you know what current is. Yeah? And you should know the units that it's measured on. And you should also know what voltage is and the difference between voltage and EMF, which remember is not a force. It's not a force. And hopefully you should also know what resistance is and that it's measured in ohms. And you should also know how to calculate current from voltage and resistance. And finally, you should also know about resistance factors. And that resistance is the resistivity times the length divided by the area. Now, before we're done, I'm going to give you a little bit of homework, which you can either give me in class or write as a comment in this website. So I want you to do this calculation. I have a potential difference of 6 volts, and then I have a certain resistance here. Now I know that I don't know the resistance and I don't know the current, but I know this. I know that the resistivity of this thing is 2 ohm meter to the minus 1. And I know that the length of the resistance is 1 meter. And I know that the area of the resistance is 2 square meters. What I want you to do is figure out the resistance and write it down in the comments. And then when you have this, use that to figure out the intensity. You're going to have to use these two equations. First this one, then this one. Good luck, and I'll see you next day. One more thing as a challenge problem. In one of these pieces of data, I have made a mistake. The challenge is to find it. See you next day.